Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So imagine turning on a machine, right? Roughly the size of a standard garden hose.
Yeah, just a regular hose.
And within the span of a single human career, you literally watch rivers begin to flow on a completely dead planet.
It sounds wild, I know.
It really does.
Yeah.
Today, we aren't indulging in some 1,000-year science fiction fantasy or, abstract philosophical thought experiment.
No, not at all. We are unpacking a rigorously detailed, paradigm-shifting mathematical model.
Right. A model that proves humanity could artificially jumpstart the Martian climate and actually reach the threshold for liquid water in just 15 years.
Which is an incredibly brief timescale in planetary terms.
Okay, let's unpack this. Because to truly grasp the sheer mind-bending scale of the thermodynamic problem we are solving today, you have to completely let go of those romanticized, red-tinted horizons you see in the movies.
You really do.
You have to step into the grim, terrifying reality of what the Martian environment actually is right this second.
It is a profoundly hostile environment.
Mm-hmm.
And understanding the specific mechanics of that hostility, well, it's the only way to understand why this new engineering approach is so revolutionary.
Exactly.
We are talking about taking a planetary body that has been ecologically dormant for billions of years and physically forcing a global climate system to boot up from scratch.
I want you, listening right now, to close your eyes and really put yourself on the surface of Mars. Just imagine standing there.
It's not a pleasant thought.
No. I mean, the average global temperature is negative 55 degrees Celsius.
And that's merely the average.
Right. If you happen to be standing there during one of the global dust storms, which, by the way, can shroud the entire planet for months at a time, the surface temperature plunges to a brutal negative 125 degrees Celsius.
You would freeze almost instantly.
And if you try to take a breath, the atmosphere is practically non-existent. It's this razor-thin, wispy layer made of 95% carbon dioxide.
Plus, if you're looking for water, you will not find it flowing.
Yeah, it's locked up, frozen solid, mixed deep within ice caps made of pure carbon dioxide.
And we can't forget the radiation.
Oh, yeah. Because there is no magnetic field and no ozone layer, you are constantly subjected to lethal doses of solar and ultraviolet radiation.
It's a constant bombardment.
And if a solar flare hits, the surface becomes utterly toxic to terrestrial biology. So Disneyland, it is not.
Grounding the conversation in those physical parameters is so essential because the magnitude of this challenge, it really comes down to raw thermodynamics.
Just heat and energy.
Exactly. When you look at the empirical data, the atmospheric pressure, the thermal inertia of the regolith, the radiation environment, you realize that Mars is not just dead. It is actively resisting the retention of heat.
It's fighting back.
Yeah, it is. The thermal inertia of the Martian surface is incredibly low, because the regolith is mostly crushed, porous volcanic rock and fine dust.
So it can't hold on to warmth.
Right. It cannot store thermal energy the way Earth's dense, moist soils or vast oceans do. Heat hits the surface, warms the top millimeter of dust for, a few hours.
And then the sun sets.
And the moment the sun sets, that thermal energy violently radiates back out into the vacuum of space.
So the planet itself is basically a giant sieve for solar energy.
That's a great way to put it.
And because the environment is so unimaginably extreme, it naturally follows that our earliest ideas to fix it were equally extreme.
Absolutely.
I mean, human beings have a psychological tendency, to look at a massive, unyielding problem and think, okay, how do we hit this with the biggest hammer possible?
The brute force approach.
Exactly. We have to talk about the brute force approach, and specifically why trying to bludgeon a planetary climate into submission mathematically fails.
The macroscopic brute force era is such a fascinating piece of our recent scientific history. For a long time, the dominant conversation around modifying the Martian climate centered entirely on highly energetic interventions.
Which brings us to the most famous proposal. You all probably know this one. Using continuous, low-fallout nuclear explosions detonated high above the Martian poles.
It's a very dramatic concept.
Very. The core idea was that these detonations would act like artificial suns, right? The intense, Localized bursts of thermal radiation would flash melt the vast carbon dioxide ice caps locked at the northern and southern poles.
Releasing massive amounts of CO2 gas directly into the atmosphere.
Right, theoretically thickening it and triggering a runaway greenhouse effect. I mean, on paper, it sounds like a decisive, aggressive stroke of engineering.
It appeals to that instinct of wanting a quick fix.
Yeah, you bomb the sky, you vaporize the ice, the atmosphere catches the heat, and the planet warms up. Boom, done.
But planetary physics does not respond to aggressive intentions. It responds to sustained thermodynamic forcing.
And that's where the math comes in to ruin the party.
Precisely. In 2018, the scientific community delivered a massive mathematical reality check that completely dismantled this entire brute force concept.
They really ran the numbers.
They did. Researchers systematically crunched the exact volumetric numbers on what the Martian polar caps actually contain, and then they mapped that against the specific heat capacity of carbon dioxide.
To see how the global atmosphere would realistically respond to that level of acute thermal forcing.
Exactly.
The numbers from that 2018 reality check are just staggering when you look at them side by side.
They are very sobering.
Let's break down the actual atmospheric physics at play here. Right now, Mars naturally possesses a very weak greenhouse effect of about 5 degrees Celsius.
And it operates at an atmospheric pressure of roughly 6 millibars.
Right, and for context, if you are standing at sea level on Earth, you are experiencing about 1,000 millibars of pressure.
So the Martian atmosphere is practically a vacuum by comparison.
And the 2018 analysis proved definitively that even if you executed this nuclear plan with impossible perfection,
Like flawless execution.
yeah, even if you utilized maximum explosive yield to vaporize every single accessible molecule of CO2 trapped at the poles, you would only push the atmospheric pressure up from 6 millibars to about 20 millibars.
Which is still incredibly thin.
It's only 2% of Earth's atmospheric pressure.
Precisely.
Right.
2%.
Yeah.
And the corresponding thermal boost from doubling or tripling that incredibly thin CO2 layer, it would only yield a 10 degrees Celsius increase to the average surface temperature.
10 degrees.
Just 10.
You'd drop continuous nuclear weapons on a planet, and your return on investment is a 10-degree bump.
It's highly inefficient.
Practically speaking, a 10-degree boost is an absolute drop in the bucket when the goal is habitability. I mean, if the average is negative 55 degrees Celsius, we need a global warm-up of at least 30 to 40 degrees Celsius just to reach the baseline required to maintain stable liquid water on the surface.
Without stable liquid water, you don't have a hydrological cycle.
Right, you don't have agriculture, and you certainly don't have biology.
The idea of brute forcing the planet with explosions reeks of this incredible hubris.
Oh, totally.
This assumption that we can easily override planetary thermodynamics with pure explosive yield. If we connect this to the bigger picture, it highlights a fundamental misunderstanding of how climates actually function.
How so?
Well, you cannot permanently alter a massive, complex fluid system through isolated, transient, energetic events.
Because explosions are just flashes in the pan.
Exactly. Explosions release a tremendous amount of energy in fractions of a second, but planetary climates are dictated by sustained, systemic changes in how continuous energy from the sun is absorbed, trapped, and circulated over long periods of time.
So it's like trying to heat a sprawling, freezing mansion by lighting a single match in the attic.
That is a perfect analogy. The nuclear approach is an acute, localized event trying to solve a chronic global problem. It is thermodynamically wildly inefficient.
Because the heat just vanishes.
Right. Because the atmosphere is so thin, the vast majority of the thermal energy from those blasts wouldn't be captured by the surrounding gas. It would simply radiate outward into the vacuum of space.
So, if macroscopic explosions fall mathematically short, if the biggest atomic hammers we can dream up fail to dent the problem, we have to rethink the scale of the intervention entirely.
We have to look in the complete opposite direction.
Right. If going incredibly big fails, we have to go incredibly small.
The shift from macroscopic brute force to microscopic precision is where the actual viability of planetary engineering begins.
And we are talking about the nanotech solution, specifically engineered aerosols.
Yes, this is the core of the new research.
This brings us to the breakthrough concept recently published by a global team of atmospheric physicists and engineers. Like, instead of nuking the poles, the proposed method involves releasing microscopically engineered aerosols directly into the Martian atmosphere.
To create what they call a sustained infrared forcing that warms the surface.
But to understand why this approach is theoretically sound, we really need to explore the exact physical nature of these proposed particles. Because, I mean, they are not just generic dust.
No, not at all. The researchers modeled two specific candidates. The first are graphene disks, which are incredibly thin, measuring about 250 nanometers in diameter.
Okay, that's tiny.
Very tiny. But the second candidate, which showed remarkable efficacy, involves aluminum rods. These are about 8 microns long and roughly 60 nanometers in diameter.
Okay, wait. Let's visualize this. An average human hair is, what, about 80,000 nanometers wide?
Roughly, yeah.
And we're talking about aluminum rods that are 60 nanometers wide. Wait, are we seriously talking about spraying microscopic glitter into the alien sky?
Mechanically speaking, yes. But it is highly engineered, thermodynamically tuned glitter.
I have to challenge this immediately. How does microscopic glitter achieve what megatons of nuclear force couldn't?
It seems counterintuitive.
Right. If the wind blows a thin layer of metallic dust into the air, wouldn't that just block the sun and make the planet even colder? Like a nuclear winter?
That is exactly what would happen if we used generic dust, which is why the precise dimensions of these particles are the key to the entire concept.
So the size is what matters here.
Absolutely. It comes down to the mechanics of electromagnetic radiation and how specific geometric shapes interact with different wavelengths of light.
Okay, break that down for us.
So the sun pumps out energy primarily in the form of shortwave visible light and ultraviolet radiation. When that shortwave radiation travels through the Martian atmosphere and hits the surface, the rock and dust absorb it, warm up slightly, and then re-radiate that energy back outward.
But the planet doesn't glow in the dark. It re-radiates that energy as heat.
Correct. It radiates the energy as thermal infrared radiation, which is long-wave energy.
Okay, short wave from the sun, long wave from the ground.
Right. The wavelength of the incoming sunlight is very short, between 400 and 700 nanometers. But the wavelength of the heat radiating off the Martian surface is much longer, typically around 10 microns.
And what happens right now with that heat?
In Mars's current state, that 10-micron thermal infrared radiation just bounces right off the surface and escapes back into the vacuum of space, because the thin CO2 atmosphere is almost entirely transparent to those specific long wavelengths.
Heat goes in, heat goes right back out.
Exactly. Heat goes in, heat goes right back out.
So the planet basically has no insulation.
None. But these engineered particles, specifically the aluminum rods, are physically sized at 8 microns long and 60 nanometers wide to exploit that exact wavelength disparity.
Okay, how?
Their physical dimensions make them virtually invisible to the incoming shortwave sunlight. The 400-nanometer light waves essentially diffract right around the incredibly narrow 60-nanometer cross-section of the rods.
So the sunlight just slips past them.
Right. The sunlight passes right through the aerosol layer and hits the surface. However, when that long wave, 10-micron thermal infrared radiation, tries to rise back up from the warm surface, it encounters a completely different interaction.
Oh. The 8-micron length of the rod is almost the exact same size as the 10-micron wavelength of the heat trying to escape.
Precisely. Because the rod is conductive aluminum and its length roughly matches the wavelength of the thermal radiation, it acts as a microscopic dipole antenna.
An antenna? That's wild.
When the long-wave infrared photon hits the rod, it excites the conduction electrons along the length of the metal, creating a localized resonance.
So it absorbs the heat.
The rod absorbs the photon's energy and immediately scatters it, effectively bouncing the heat back down toward the surface rather than letting it escape to space.
Wow.
Yeah, they have a drastically stronger interaction with thermal infrared than with visible sunlight.
So, to use an analogy, we aren't just putting up a physical wall. We are creating a high-tech, one-way thermal blanket around the entire planet. Or a mirror.
Yes, a thermal mirror.
The mirror lets the shortwave solar heat come in freely, but when the planet tries to radiate that heat away as long-wave energy, the microscopic antennas catch it and bounce it back down.
That is the exact mechanism. You are fundamentally changing the rules of how energy moves through the Martian thermodynamic system.
It's so elegant.
It is a sustained, systemic alteration of the planet's radiative balance. And here's a crucial detail regarding the engineering parameters. These specific particle shapes and materials, the 250-nanometer graphene disks and the 8-micron aluminum rods, they were not even perfectly optimized for warming yet in these initial computational models.
Wait, really? They could be better.
Yes. The researchers simply picked strong, known candidates to prove the underlying physics of the concept. The incredible thermal results we are about to discuss don't even represent the absolute upper limit of potential heating.
That's crazy.
If material scientists further tune the geometry, the aspect ratio, and the composition of these aerosols, the scattering efficiency could increase significantly.
That is a fascinating caveat. We are looking at baseline proof of concept numbers. But having the idea for a microscopic antenna is one thing, right?
Sure.
Predicting how trillions of these particles will behave across an entire planetary atmosphere is another. Because historically, didn't previous scientific models look at aerosol warming and determine it was, too inefficient to work?
They did. But those historical models were hobbled by their computational limitations. They were overly simplistic. Well, earlier models analyzing aerosol distribution essentially assumed that if you release these particles, they would instantly form a static, unchanging, perfectly even layer across the entire sky.
Like installing a rigid glass dome over the planet.
Yes, exactly like a glass dome.
Which makes no sense because an atmosphere isn't a solid object, it's a fluid. It's constantly churning, mixing, rising, and falling based on temperature and pressure differentials.
Exactly. The earlier static models were useful for basic proof-of-concept mathematics regarding radiative transfer, but they could not tell you if the intervention would actually function in a real turbulent planetary environment.
And this is the pivot point of the new research. Here's where it gets really interesting, because this is where the models caught up with the theory.
They moved from a static, idealized assumption to a highly sophisticated three-dimensional global dynamic model.
And the defining feature of this new simulation is a computational technique called plume tracking. Let's dig into what plume tracking actually means for the average listener.
All right, so plume tracking is the computational ability to follow the movement and dynamical behavior of the engineered aerosols over time within a fluid system.
You aren't just magically teleporting a uniform layer of particles into the upper atmosphere.
No, in reality, you are releasing them from specific, localized point sources on the surface.
Like factories.
Perhaps industrial atmospheric processors stationed near the equator or the poles.
Okay, and then what?
The 3D model calculates exactly how those specific particles are lofted into the air by local thermal updrafts, and then how they are caught and carried globally by massive Martian atmospheric currents, like the Hadley cells.
Wow, so it turns a sterile mathematical equation into a living, breathing weather model. It calculates the actual wind.
Yes, the wind dynamics are fully integrated.
And what I found so compelling is how it simulates what they call radiative dynamical feedbacks.
What's fascinating here is that those feedbacks are the engine of the entire process.
Right, because as the particles trap heat, they artificially change the temperature of the air immediately around them.
And warmer air expands and rises.
Exactly, which changes the local air pressure. Changes in air pressure create new wind currents, which then grab the particles and move them further around the planet, spreading the heat even more.
The fluid dynamics reveal that the atmosphere itself does the heavy lifting. You don't need to engineer a fleet of 10,000 specialized aircraft to fly all over Mars, evenly dusting the sky day and night.
The wind does the work for you.
The planet's own convective currents naturally distribute the thermal blanket. You introduce the aerosols at key strategic locations, and the induced thermal gradients create the very winds that spread them globally.
But wait, Mars isn't a pristine, empty wind tunnel. Mars already has massive amounts of dust in its sky. I mean, we've all seen the rover pictures of the hazy red horizon.
Very true.
How can a model confidently predict how microscopic aluminum antennas will behave if they're constantly smashing into naturally occurring Martian dust?
That is a critical variable, and it is precisely why the researchers didn't model the aerosols in a vacuum.
They included the dust.
Yes. To make the simulation as realistic as computationally possible, they integrated a time-varying background of natural Martian dust into the 3D model.
Because natural dust traps heat too, right?
Natural dust also interacts radiatively with sunlight and heat. It absorbs some energy, blocks some visible light, and emits its own infrared radiation.
So they had to calculate the thermal interference of the natural dust fighting against the engineered particles?
Exactly. They utilized a massive observational database compiled from a relatively storm-free period on Mars to understand precisely how these new artificial aerosols would interact with the natural, messy thermal environment of the planet.
That is incredibly thorough.
By integrating the natural dust cycles, the complex local topography of mountains and deep craters, the changing seasons, and the fluid dynamics of plume tracking, well, they established a highly credible simulation.
A simulation of what would actually happen if we flipped the switch on this technology today.
Yes.
Which naturally brings us to the most pressing question for anyone listening to this.
The timeline.
The timeline. The model is brilliant. The physics of the aluminum antennas check out. The fluid dynamics show the wind will spread them. So if we actually land the machines on Mars, load them up with aluminum nanorods, and turn the system on, How long does it actually take to see a return on this investment?
That's the million-dollar question.
Because the prevailing assumption regarding terraforming is that it is a multi-generational project. People assume we are talking about thousands or tens of thousands of years to even begin seeing frost melt.
That has always been the baseline assumption, yes. But the timeline revealed by this dynamic model is shockingly, almost unbelievably fast.
Let's walk exactly through the timeline and the release rates proposed in the simulation, because the numbers sound like a typo at first glance.
You really do?
The model specifically focused on the continuous atmospheric release of 3 liters per second of these IR-active aluminum particles. Let's pause and visualize that volume. 3 liters per second.
Is that a lot?
No, that is roughly the flow rate of a standard residential garden hose. We are talking about pumping out a garden hose worth of metallic material, starting at the planet's northern equinox.
It seems like an infinitesimally small volume of material when compared to the vastness of an entire planetary atmosphere.
A single hose for a whole planet.
But because these particles are microscopic, measuring in the nanometers, 3 liters per second equates to trillions upon trillions of individual heat-trapping antennas entering the atmosphere every single moment.
Trillions a second. Okay, so milestone 1. We turn on the garden hose. According to the 3D model, within less than 4 Martian years, which translates to roughly 7.5 Earth years, that single continuous source stably saturates the entire globe.
That's the global saturation point.
In less than a decade in Earth time, the newly created wind currents have taken this single stream of material and wrapped the entire planet in a functional, globally distributed thermal blanket.
And just to clarify, the researchers tested release rates between 0 and 60 liters per second. But the model showed that a mere 3 liters per second is sufficient to reach global saturation.
Why is that saturation point so important?
Reaching that global saturation point is mathematically critical. It signifies that the fluid system has achieved a steady state where the atmospheric particles are distributed evenly enough and densely enough to exert a globally uniform radiative forcing.
Rather than just localized hotspots.
Right. You need the whole planet covered.
Which sets the stage for milestone 2. Around 8 Martian years into the continuous release process, this is where the thermodynamics cross the threshold. At 8 Martian years, the global surface temperature drastically jumps.
It's a very sharp increase in the model.
It rockets from a sluggish baseline of 3 to 4 degrees Celsius of warming, all the way up to roughly 25 degrees Celsius above the unperturbed temperature.
That sudden nonlinear jump is indicative of a massive thermal feedback loop finally catching. The lower atmosphere traps enough continuous heat that the planetary dynamics permanently shift into a warmer equilibrium state.
The ground itself begins to retain heat rather than instantly radiating it away.
Exactly.
And then we hit the final milestone. Around 15 Martian years after we flip the switch, the temperature stabilizes at about 35 degrees Celsius of total warming. Let's just sit with that number for a second.
It's incredible.
35 degrees of systemic planetary warming. That is the magic threshold. That single jump brings the agonizingly freezing average temperatures up to a point where you can maintain stable liquid water on the Martian surface during the warmer seasons.
15 Martian years. Roughly 30 Earth years.
30 years.
It is a profound paradigm shift in how we conceive of planetary engineering.
I have to play the skeptic again here. 30 Earth years to completely overhaul the climate of a planet that has been frozen for 1 billion years.
I understand the skepticism.
I mean, we can barely predict the effects of a 1-degree shift in Earth's climate over a century. How can this model confidently project a 35-degree shift in a few decades without the entire atmospheric system tearing itself apart in unpredictable ways?
The speed of the transformation is precisely because the Martian atmosphere is currently so incredibly thin.
Okay, explain that.
On Earth, the oceans and the incredibly dense atmosphere act as massive thermal buffers. They absorb massive amounts of energy, which slows down global temperature shifts.
Like a heat sponge.
Yes. Mars lacks that thermal buffer entirely. Its thermal inertia, as we discussed earlier, is practically zero.
Right.
Therefore, when you aggressively change the radiative properties of the atmosphere with these aluminum particles, the surface temperature responds almost immediately. The lack of a buffer makes the planet highly responsive to forced thermal changes.
So what you're saying is because Mars is effectively a blank thermodynamic slate, it reacts incredibly fast to whatever inputs we give it.
Exactly. And the time scale of this thermal response proved to be almost entirely independent of the actual release rate of the particles.
Wait, really? So pumping more particles faster doesn't speed up the warming?
And not significantly, no. Whether you pump 3 liters per second or 60 liters per second, the planet still requires roughly those 15 Martian years
Yeah.
to undergo its fundamental thermodynamic absorption process.
Why?
The regolith has to absorb the heat layer by layer. Pumping more particles just ensures a thicker optical depth, but it doesn't force the rock to absorb heat any faster than its physical properties allow.
Ah, I see.
Furthermore, the resulting warming proved remarkably stable across the simulation, varying only modestly by season, fluctuating by about plus or minus 5 degrees Celsius.
It's like turning an oven on to cook a massive roast. You can't just blast the oven to 1,000,000 degrees to cook the meat in 3 seconds. The heat has to physically permeate the mass of the roast at its own rate.
That's right.
The planet has to absorb the energy. But still, the speed is awe-inspiring. If terraforming is a 10,000-year project, it's a philosophical pursuit for our distant descendants.
Yes, it's abstract.
But if it's a 30-year project, it is a practical engineering objective for people alive today.
It entirely rewrites the cost-benefit analysis of Mars colonization. However, we must heavily temper this excitement by introducing the concept of atmospheric reversibility.
Uh-oh. What does that mean?
Because the atmosphere remains relatively thin even with the aerosols, and because the system lacks deep thermal buffers like oceans, the newly engineered climate is incredibly fragile.
Fragile how?
The dynamic model clearly demonstrated that if the continuous aerosol release is terminated, say, just before that sharp temperature jump at year 8, the atmosphere loses its insulation and reverts to its freezing pre-release state incredibly quickly in just 4 Mars years.
Wow. 4 Martian years and all that progress is erased. So you can't just get the planet halfway warmed up and decide to take a 10-year hiatus to secure more funding.
Absolutely not. The engineered particles possess mass, and eventually gravity and natural atmospheric scrubbing pull them out of the sky and deposit them onto the surface.
They just fall out of the air.
If you do not maintain the garden hose to continuously replace the particles that fall out of suspension, the thermal blanket thins out, the trapped long-wave infrared radiation escapes back to space, and the planet rapidly plunges back into a deep freeze.
It requires absolute, unyielding, continuous commitment.
You are essentially putting the entire planet on artificial life support until it can naturally generate its own thick atmosphere.
Which introduces a terrifying sociopolitical variable into the physics. Imagine the geopolitical funding gets cut back on Earth. The resupply ships stop delivering the raw aluminum, the atmospheric processors run dry, and within 8 Earth years, your entire newly thawed ecosystem freezes solid again.
That is the precarious reality of artificial climate forcing.
And that fragility leads us perfectly into the ultimate reality check. Because nature, as we know all too well, rarely behaves perfectly according to a sterile computer simulation.
There are always wildcards.
Exactly. If the planet is reacting this incredibly fast to the thermal forcing, what are those wildcards? What are the chaotic, nonlinear elements that could derail or even uncontrollably accelerate this entire carefully calculated process?
This is exactly where planetary science transitions from a clean engineering blueprint into an exercise in managing chaos.
Managing chaos, I like that.
The authors of the study are extremely transparent about the acknowledged limitations of their simulation. They emphasize that atmospheric processes are inherently complex, nonlinear dynamical systems.
And several massive open questions remain.
Yes. They specifically highlight 2 critical areas of uncertainty: water cycle feedbacks and agglomeration mitigation approaches.
Let's dedicate some serious time to exploring these physical feedback loops, because this is where the planet fundamentally fights back against our engineering.
It is.
Let's start with the positive feedback loop, water vapor. As the aluminum particles do their job, the lower atmosphere warms up and eventually breaches the freezing point of water. We know there's vast amounts of frozen water ice locked in the Martian regolith and the poles. So the ground warms, the ice melts, and water vapor begins to naturally enter the atmosphere.
And water vapor is a remarkably potent natural greenhouse gas. In many atmospheric conditions, it is far more potent at trapping heat than carbon dioxide.
Okay, so follow the chain of events here. You spray the aluminum antennas, the planet warms up, the ancient ice melts, water vapor fills the air.
Right.
Now that newly liberated water vapor starts trapping even more heat alongside your aluminum particles. This triggers a runaway compounding warming effect. The planet starts heating itself far faster than the 3D models initially predicted.
From a purely goal-oriented engineering standpoint, A positive feedback loop like that might initially be seen as a massive benefit.
Sure, it does your work for you.
It does your work for you and dramatically accelerates the terraforming timeline. But from an atmospheric management perspective, it introduces severe instability.
How so?
If the planetary surface warms too rapidly and massive volumes of water vapor are injected into an atmosphere that is not thermodynamically prepared to handle them, you could trigger extreme global weather anomalies.
Like what?
You are talking about unimaginable storm systems, hyperhurricanes, and chaotic convective turbulence as the frozen atmosphere violently thaws.
You essentially lose control of the thermostat.
You do.
Okay, so that is the danger of the positive loop. But then there's the negative loop, which honestly sounds like the ultimate project killer, the issue of cloud nuclei and agglomeration.
Yes. This involves the complex microphysics of atmospheric condensation.
Tell us about that.
When you pump trillions of highly engineered aluminum nanorods into an upper atmosphere that is suddenly gaining massive amounts of water vapor from the thawing ground, those artificial aerosols might inadvertently act as cloud condensation nuclei or ice nuclei.
Meaning, the newly liberated water vapor looks at these trillions of little 8-micron aluminum rods floating in the cold upper sky and says, hey, a perfect solid surface to condense onto.
Precisely. In the freezing upper reaches of the Martian atmosphere, water vapor, or gaseous carbon dioxide, could easily condense and freeze directly onto the surface of the aluminum particles.
And this physical clumping process is known as agglomeration.
Yes.
Agglomeration. Let's visualize how agglomeration actually destroys the system. Think about how a hailstone forms in Earth's atmosphere. You start with a tiny speck of dust high in a thundercloud. Supercooled water droplets freeze onto that speck.
Layer by layer.
Right. The updrafts push it around, more water freezes onto it layer by layer until the hailstone becomes physically too heavy for the aerodynamic lift to support it, and gravity forces it to plummet to the ground.
That is a very accurate comparison.
That is exactly what agglomeration threatens to do to our thermal blanket. We have these perfectly engineered 60-nanometer rods, mathematically designed to be aerodynamically light enough to ride the Martian wind forever. But suddenly, they get coated in thick layers of heavy ice.
They lose their calculated aerodynamic lift-to-drag ratio. They become heavy, irregular clumps of ice and metal, and gravity simply pulls them straight out of the sky.
They rain back down to the surface, and the thermal blanket essentially destroys itself from the inside out.
And the mechanical failure goes even deeper than just falling out of the sky. Even before they fall, they lose their specific radiative properties.
Oh, because the shape changes.
As we discussed earlier, the 8-micron length and the conductive nature of the naked aluminum are what make it function as a perfectly tuned long-wave infrared antenna.
Right.
If you encase that precisely tuned antenna in a thick, irregular shell of water ice, it fundamentally alters how the particle interacts with electromagnetic radiation.
So it stops bouncing the heat back.
Exactly. A massive clump of ice-covered aluminum does not cleanly scatter 10-micron thermal radiation the way a naked rod does. It might actually start reflecting incoming sunlight instead.
Which would actively cool the planet.
Yes, it could reverse the warming entirely.
So the entire mechanism breaks down simultaneously. Imagine you are running this terraforming project. You are sitting in mission control on Earth, watching the telemetry.
It would be incredibly stressful.
How do you possibly balance spraying enough particles to warm the planet, which inevitably melts the ice, without accidentally triggering a runaway cloud condensation effect that coats all your perfectly engineered particles in ice, ruins their optical resonance, and makes them rain back down to the dirt?
This raises an important question. It is the ultimate atmospheric balancing act, and it deeply connects to the limitations we face right here on Earth.
Oh, interesting. How so?
If we compare this highly advanced Martian dynamic model to Earth's own global climate models, we see the exact same chaotic variables at play. The behavior of atmospheric aerosols is notoriously one of the most complicated and poorly understood facets of climate science. Oh yes, on Earth, climatologists rigorously study how anthropogenic pollution, volcanic ash, and natural sea salt aerosols interact with cloud formation. Those interactions push and pull the global climate in every direction simultaneously.
So it's unpredictable?
Highly unpredictable. Sometimes aerosols cool the Earth by reflecting shortwave sunlight. Sometimes they warm it by absorbing long-wave heat. Sometimes they act as condensation nuclei and create massive rainstorms.
And sometimes they do the opposite.
Sometimes they suppress precipitation entirely. by creating droplets too small to fall.
And on Mars, you have to throw the natural dust loop back into that chaotic mix.
Exactly.
A rapidly warming Martian atmosphere means more thermal energy injected into the fluid system. More energy means stronger, more turbulent surface winds.
Which picks up more dust.
Stronger surface winds inevitably elevate vastly more of the natural red Martian dust high into the atmosphere. And that natural dust also traps some heat, blocks some visible light, and acts as its own condensation nuclei,
Creating yet another highly unpredictable interacting feedback loop with your artificial aluminum system.
It is a dizzying, multi-layered web of thermodynamic cause and effect.
It is the textbook definition of a nonlinear dynamical system. You pull one single lever, in this case, releasing 3 liters per second of aluminum rods, and 50 other levers across the planet begin to move entirely on their own.
Like dominoes.
Exactly. The hydrological cycle, the natural dust cycle, the global atmospheric pressure, the wind shear, they all begin to interact in ways that even the most advanced quantum supercomputers struggle to predict with absolute certainty over multi-decade timeframes.
So how do we even prepare for that?
To make this reality, we have to study agglomeration and mitigation approaches extremely aggressively.
Like preventing the ice from sticking in the first place.
Right. Materials engineers have to figure out if we can chemically coat the aluminum aerosols in a hydrophobic polymer so water vapor simply cannot stick to them.
Oh, like a Teflon coating for the antennas?
Essentially, yes. Or meteorologists have to calculate if we must constantly adjust the specific altitude of the release points to intentionally keep the particles above or below the forming cloud layers.
It is just a staggering level of complexity. When we synthesize the sheer volume of chaotic variables and precise mechanical details, from the quantum physics of plume tracking to the aerodynamic drag of ice-coated nanometers, it inevitably moves the conversation from the raw mathematics into the profound philosophical implications of wielding this kind of localized power.
It does. We are no longer just talking about exploring a planet. We are talking about becoming active, deliberate planetary architects.
It represents a profound, irrevocable transition in human capability. We are moving from observing the universe to fundamentally rewriting its local thermodynamic laws.
It's an incredible thought.
To summarize the massive, mind-bending journey we have just taken together, we started on the surface of Mars as it exists right this second. A brutal, freezing, radiation-soaked dead rock with almost zero thermal inertia.
An incredibly hostile place.
We looked at our early, aggressive engineering instincts, the brute force nuclear options, and discarded them. Because the universe does not care about explosive yield. It only cares about sustained thermodynamic forcing.
Exactly right.
And from that failure, we discovered this highly modeled, incredibly rapid, microscopic solution, engineered aerosols. Billions of aluminum nanorods acting as tiny tuned antennas released from a machine the size of a garden hose.
Catching the Martian convective winds.
Wrapping the planet in a one-way thermal mirror and potentially bringing stable liquid water back to the surface in just 15 Martian years.
It is a stunning testament to the power of human ingenuity, the precision of modern materials science, and our rapidly evolving understanding of complex atmospheric fluid dynamics.
You listening to this right now understand the absolute cutting edge of planetary climate engineering. You know exactly how tiny metal rods interacting with long-wave infrared radiation and the fluid dynamics of an alien atmosphere could literally build a new, habitable world from scratch in the span of a single human career.
And there is a much deeper, more immediate resonance here that we must acknowledge.
What's that?
Because understanding the precise microscopic mechanisms required to build a habitable, stable climate on Mars inherently makes us infinitely better equipped to understand the delicate, interlocking climate feedback loops right here on Earth.
Oh, wow. Yeah.
The fundamental equations governing radiative transfer, fluid dynamics, and aerosol condensation are universal. By aggressively stretching our computational minds to solve the extreme puzzle of warming Mars, we refine the exact mathematical models and atmospheric physics we desperately need to monitor, deeply understand, and perhaps successfully protect the fragile climatic balance of our own home planet.
The knowledge is intimately, inextricably connected.
It really is.
Which leaves us with one final lingering thought. Something I really want you to mull over long after you finish listening today.
Curious.
If humanity actually developed the technological mastery and the precise computational models to perfectly tune the climate of a dead world millions of miles away, does that unprecedented capability give us the ultimate responsibility to go out into the dark and do it? Or does it simply prove once and for all that we have always possessed the power and the ingenuity to perfectly stabilize the one magnificent world we already live on?